the Conservation Department purchased a portable X-ray fluorescence analyzer, courtesy of the 1956 Otto Haas Charitable Trust. Today I will describe what XRF is, how we've started using the technology, and what we hope to develop out of it. The Women's Committee endowment for staff development allowed me to attend a workshop in the spring on XRF. So I started getting my feet wet with this technology, and that's what I plan to share with you today. The Bruker Tracer 3SD that we purchased arrived in 2 cases full of cables and parts, and I went through the packing list and the instrument manual to identify what everything is. And this is what it looks like when it's ready for action. What is XRF? It's a non-destructive analytical method for identifying elements. It doesn't give us information about compound structures or organic molecules, but it does tell us what elements are present. The technology has been around for some time. It was first mentioned in the conservation literature in 1958, but recent advances in the technology has made it portable and far more affordable, so it's becoming more and more widely used in our field. So this is how the analyzer acquires the data. First, it bombards the sample with X-rays. Then the X-rays excite some of the electrons from the inner shells and eject them, creating voids in the atom structure. Because it's most stable when the inner shells are full, outer shell electrons drop to fill those voids. And as the electron drops, it emits characteristic energy that is then detected by the analyzer. The energy emitted by the transitions between the 2 shells are characteristic for each element, so we can identify what's present in the sample based on what those energy emissions are, on the specific energy emissions. So what elements can we see? XRF is great for detecting medium and heavyweight elements, but we lose the ability to see things at the lighter end of the periodic table. If we draw a vacuum, we can increase the range of what we can see. So sodium and magnesium are sort of borderline. It can be tricky to get that far. And there are also complications with some of the other lighter elements that have overlaps with different lines from some of the heavier elements. So how can portable X-ray fluorescence help us here at the museum? It's a great tool for pesticide testing. It can help us learn about what pigments are used in our materials here. We can use it to assist with metals analysis, ceramics analysis, glass analysis, and we're learning about other areas of research that we can use XRF for as well. For pesticides, heavy metals were commonly used until as late as the 1970s. We know that heavy metals were used as pesticides here at the museum on our collections. This is not usually very well documented, and pesticides, when they're applied in various methods, are typically not very visible unless they're applied in huge quantities, which I think we might have an example of that here. I'm sure we do. But since it's not well documented and not visible, we don't know what artifacts were treated with pesticides and what wasn't. Because of that, because the heavy metals are persistent, they don't evaporate, they don't disintegrate, they stay present. It's important for us to know whether or not they're present because they're toxic to us as people. And a specific case where that is more important, because at a museum here, we know that pesticides were used, we can protect ourselves, but we also repatriate some of our artifacts. And typically the ones treated with heavy metal pesticides are organic, Many of them are in the American section, also in the Oceanian section. And if we're going to return material to Native people, we need to inform them about how they need to protect themselves as well. Here's an example. So we know that heavy metals, specifically arsenic, was purchased in relation to the Borneo collection. This leopard seed mat is part of that collection, but we didn't know specifically whether or not it had been treated with pesticide. So we did a test with the pXRF, collected spectra, and we found a very prominent and unmistakable peak for arsenic. Now that we know that it's been treated with arsenic, we can take measures to protect ourselves. One, in addition to all the other wonderful benefits of bagging artifacts, bagging gives us a barrier, a physical barrier between us and the toxin. It also prevents the spread of arsenic and transfer by physical contact onto other objects. We've now labeled the object, we've documented that it's been treated with arsenic, so we can inform anybody who's handling or working with the collections to wear gloves and to not touch their face while they're working with it. So it's really useful for us for our own health and safety. Many pigments, most pigments are, they have a metallic element that produces the color in the pigment. And you can see from this short list, there's many different ways to produce the same color. pXRF allows us to identify what those elements are, and it gives us better insight into the manufacture of the artifact. Knowing what the element is doesn't always give us positive pigment identification, but it gives us a great way to narrow the field of questions that we then can ask. And if we need more analysis to determine specifically what something is, then we can ask very specific questions. Here's an example where pXRF really helped us narrow down the field of what these pigments are. We can say that the red is vermilion because mercury is present, and mercury is the main component in vermilion, and it's not used for making other pigments. So we can be pretty confident to say, you know, red, lots of mercury, vermilion. But the yellow is a little bit more interesting. We found barium, we found lead, and we found chrome. So what does that mean? It could be barium yellow with a lead extender. I believe lead sulfite was a common extender. Or it could be chrome yellow with barium sulfite as an extender. Or it could be a mixture of barium yellow and chrome yellow. So it gives us it focuses the next question. So we know that the yellow contains barium, lead, and chrome. We've limited the number of possibilities of what it could be. And the question is, do we need to know more? Well, that depends on how specific you need to get. Here, barium yellow and chrome yellow were both used in the mid-19th century. That narrows down our field for when this robe would have been made. We know it was made some point after 1803, when these pigments first came into use. And we know that it's likely that it wasn't made into the 20th century because those pigments gave way to preference for cadmium yellow, for example, and they weren't used much later. I think there are some instances where they are. I believe barium yellow is used in the highway paints, but that wouldn't be an application here. So that answers a question of what time range are we looking at in the production of this piece. Do we need to know more than that? So that's a really good question. If we do, then we can look to other analytical techniques to pinpoint the crystal structure and then identify, yes, is it barium yellow, or is it chrome yellow, or some combination thereof. pXRF can be an aid in ceramics analysis. This is a pot A. I forget the full title, but this pot comes from Chang, which we heard about last week, the site that we heard about last week. XRF is good for aiding in determining slip composition and glaze composition. It can be used for knowing more about the clay body, but XRF samples are best when they're infinitely thick and uniformly homogeneous. And ceramic, being a heterogeneous material, is not the ideal for telling us about the clay body. If we want to use that technique, then taking a sample is appropriate, would be the way to do it. And if they were taking a sample, there are other techniques that we could also employ. In the case of slip, XRF being a surface analysis and slip being very difficult to sample, it gives us a way to distinguish between components that are in the slip and not in the underlying ceramic. And here's an example from a shirt from Cheshma Ali, and you can see in the detail on this side that there's a significant increase in the amount of magnesium between areas that were sampled, or areas that were tested with versus without slip. Iron, which is the peak right next to the magnesium, can sometimes interfere with that, but since iron we can see is held constant, that change in volume can be attributed to the slip and the colorant used to create it. For glass analysis, XRF can aid in identifying what flux is used in the glass composition, if there are any stabilizers, what the colorants are. It's also, by knowing what the elements are and using our visual analysis, we can start to narrow down or classify the different types of glasses that we have. It's controversially used for obsidian sourcing. There are two well-respected scholars that are debating. They both use the technique. They both claim that sourcing is possible, and they come to very different conclusions. So while they're fighting it out, we're keeping an eye on that, and we are we know that we can get elemental information, but how far we can use that information and interpret it to come to a specific meaning is something that is still developing right now. In the same way, XRF can help with metal analysis to find out what elements are present, of course. And this is useful to distinguish between modern and ancient alloys. XRF, when you have standards to work against, can be used for semi-quantitative and quantitative analysis. This is an area that we're still learning about with our new equipment, and we hope that the workshop that we'll be holding, we can explore this deeper and develop that. In semi-quantitative work, if you have a group, you can compare objects within that group, but it's much more difficult to compare objects to other groups and other people's work. And quantitative analysis allows you to make that leap. So if we can get that far with our XRF, we'll be quite pleased. But here's an example of how we are able to use comparative knowledge between two different objects that were analyzed with the same technique. And Christopher Thornton and Holly Pittman were interested in knowing if their identifications, whether something was prehistoric or Islamic, were reasonable identifications to make. So we used XRF to analyze a group, I think there are 12 objects or so, and to say, use that information to support their identifications. Later copper alloys have tin or zinc to give it different properties of strength and use. And so when we see bronzes and we see brasses, specifically brasses with the zinc component, then we know that that was made later. And when we see copper that has some inclusions from natural occurring or elements in the ore, then while we can't necessarily say this could only have been made in prehistoric time, we can say that it's consistent with what could have been made in prehistoric time. And if you look at these spectra, this enormous peak there, that pair of peaks is for copper. And everything else, so these are not on a one-to-one scale. I did not have the opportunity to make them in the same comparative image like with the slip so that you can compare them. But if you look at, this is the same peak in the spectrum. And if you look at how small it is and how big these other elements are in comparison, these elements here are just traces of other inclusions in the ore. And here you specifically see zinc, tin, and here you specifically see zinc. So Holly and Chris have done a good job and classifying this as prehistoric and this is Islamic, because we don't see these types of alloys until later on. So why do we want to know this information? We've discussed about pesticides and how we can protect ourselves against it when we know that they're used, and we can also protect our collections. And this Taoist figure from China is a fabulous example to explain that idea. It is made from realgar, and realgar is essentially an arsenic mineral that will deteriorate over time, accelerated by exposure to light. So we get two hugely important pieces of information. So knowing that there's arsenic present, we know that we need to protect ourselves. We should wear gloves, we should label it so that others who might be handling it are informed and can protect themselves as well. Knowing that it's realgar, knowing that it's arsenic and that this is a realgar object, realgar, by exposure to light, it has a disintegrative property that over time it will reduce to powdered realgar and eventually turn to powder, and light significantly increases that deterioration rate. So we know that we need to keep this object out of light. And in general, knowing what our objects are made out of and understanding our collections better allows us to use them and put them in context, learn about our material culture, take that knowledge to inform the general scholarship that is what we do here at the museum. And XRF is a fantastic tool to do that. It's not the only tool. There are several other tools. I'm not going to go through this list. It's not close to exhaustive. There are many more that are not even on this list. But what you will notice is that there are several denoted with an asterisk. Those are techniques that we find very useful, but are in some way or another destructive. And since we're stewards of our collection, protecting our material culture, taking a sample should not be done lightly. And the smallest sample, if we do need to take one, is preferable to any large samples. Using XRF, we can make decisions on whether or not a next step is necessary, because one of the great advantages of XRF is that it's not destructive. It has little to no preparation time. When you're using a portable unit, you line it up against the surface or as close to the surface as you can without disturbing it, and it's portable. We have so many materials in this museum that are very large, very difficult to get from one part of the museum to the other. Some of our material is very fragile, and if we can avoid moving it, we can protect it. So by being able to bring the equipment to the artifacts, that's another advantage that this type of portable unit affords us. And now that the technology has gotten more affordable, it's far more affordable than compared to other techniques. We're also working on developing quantitative parameters. This is something that we chose an instrument that gives us a high level of control, and we can really fine-tune the parameters that we are asking of it. But that means that we also need to do our own interpretation and build our own parameters, whereas there are other units that will spit out a number, but that unit is not necessarily primed to give you the most information for the types of materials that we're looking at. Those are designed for industrial uses, for single applications. To get the range of material and the range of questions, we need to really be able to control what we're doing. Some of the disadvantages of XRF is that it's a surface analysis only. It can't distinguish between layers when you have a thin layer. So by surface analysis, it can penetrate depending on what the radio opacity of the material is. And if there are multiple layers within that area that the XRF can activate, then it can't distinguish between those layers. And as we saw earlier in the periodic table, that there are some very light elements that XRF can't identify, even if we do draw a vacuum. And the ones that we can see can have interference from some of the heavier metals, or heavier elements. So we need to be very careful with the light elements that we are, in fact, saying something that we can identify and see. And then XRF has a limited spot size, and that limitation is both in its largeness and its smallness. It can be too large. You can't pinpoint a single grain or a single tiny spot like you would when you're, for example, looking at a ceramic cross-section. There you want to identify what every grain is, and that spot size of XRF is too large to distinguish between them. But it also has too small a spot size that you can't get gross information about a large body that's heterogeneous, and you don't know if you're going to get all the information that may or may not be present. What are some of the future possibilities that we hope to use our equipment is that, as I mentioned, we're developing techniques and parameters for doing semi-quantitative and quantitative analysis. That's what we're actively working on now. We'd like to systematize some of our pesticide screening methods so that we can identify them, and when things are repatriated, use that knowledge and the things that I spoke about earlier. And XRF affords collaboration between various people in the museum, various departments, various interests. By pulling those resources together, we can then paint a much larger picture. And this buffalo robe is a great example that XRF gives us a certain material knowledge that you also need curatorial knowledge to find out why is this important and why is this relevant. And we're actively looking for other possible applications, and our aim fundamentally is to better understand our collection so that we can use it and share it. So today's talk was short and sweet. And thank you very much. And if there are any questions, I'm happy to.
What is the slot beam size?
It's a few millimeters, and I have that documented with the equipment, but if you want to know more, I can email that to you.
Well, I'm going to be at the workshop.
Okay. But it's about, probably about ½ a centimeter, but I can look that up specifically.
Okay.
Gotcha.
But the thing about the spots, small spot size, it seems like the buffalo robe, you moved it all around because you
Right.
get brown colors, so I mean you can get over that a little bit, can't you? Just
Right,
like
you can.
if there's a visible difference
Right.
in color. But my other question was, I think you had a bullet item that you can't use it for sourcing. Why is that?
Well, you can and you can't. And are you talking about obsidian or ceramics?
It was in one of your slides.
Yeah,
it was-
metals analysis. It was that you couldn't
Oh,
use
in
it
metals.
for
Well,
ore
metals
sources.
are so manipulated. They go through high processing that any information is lost in the production method. Any of that type of information is lost in the production.
Which means things get mixed in together.
Things get mixed and homogenized and things get burned out. Rare earth elements are very useful in sourcing, but in metals they don't survive the processing. So they're not there for us to look at.
And metal ore bodies are so heterogeneous that
From one place in the ore, in the mine to
Exactly.
the other, you get different results
Very,
too,
very different.
right?
okay.
Right. Thank you, Elizabeth.
In the case of obsidian, if you knew that there was a limited number of possible sources and their sort of profiles were known, would you be able to do it?
Yeah, you may, and that's exactly what the debate is. They're two different results. So when you have the same sample and two different respected people say they come from different sources, that's that's where the problem is. But that's actively being researched, and we can gather the information and decide whether or not that's enough for us. But it's not something that you can say, yes, I can do it. We can try.
And one thing about with any of these analytical things, just saying, is once we have the data, the more people start developing the data, you get to a certain critical mass where you start understanding things. And one of the great things about the combination of now having this instrument and EMU is that we will be storing all of the information that we get
That's right.
from the pXRF. And Nina can sort of explain a bit more what she's been doing with that.
Well, I've been storing the files right now just separately, but I've been trying to write reports on what it is that I have found and put at least the screenshot of the spectrum. Because the spectrum is the data that you can then use to extrapolate further conclusions. So yeah, I've been attaching those records as documents in the multimedia file, or in the multimedia module, and then attaching them to the individual collection modules. I collected a lot of data that I have yet to process, and some of the questions require semi-quantitative analysis that I'm still in the process of learning. So I'm hoping that in October, when we hold this workshop, I'll be able to ask targeted questions to resolve some of the issues that I'm having with answering questions. I know the Mediterranean section, for example, gave me a few objects to decipher for them, and I think that's possible, but I need a little more information before I can draw conclusions.
I'm worried this is going to sound like a joke question, but I'm totally serious. Shouldn't you be wearing hazmat stuff when you're doing this?
It's not a joke question. So the XRF emits X-rays between 0 and 40 kV. The unit is shielded within the analyzer so that it's only coming out from the spot location. So once you've reduced all of that, you have essentially ambient radiation that you're getting from going on an airplane. And the radiation used is less than what you get at the dentist, or it doesn't penetrate it doesn't go very far, and it doesn't penetrate very deeply. So when you have a sample blocking the X-ray path, the X-rays can't even get through the sample. So we've tested with a Geiger counter all around. It's been verified, but it's not a joke question. It's a very good question.
Do not let her point it at your chest and pull the trigger.
Thank you. There's a documented angle at which the X-ray beam is highest, and even when it's idle, it's best to avoid that area. But normally, when it's idle, we either keep it covered or we turn it off. So that's right. That's a good question.
But they used to, when you were using X-ray machines, have those
Wear
little film
badge.
badges because of the shielding, and that kind of thing's not required anymore.
Well, we're not,
I think it's both the question of the shielding and the X-ray source is different than it used to be.
right.
The old ones were much hotter than these new ones.
And those shields are also often used for industrial size X-rays when you're shooting 300 kb through a block of stone, for example. This is a fraction of that and it doesn't travel that far. It's not actually, not a bad idea to monitor. But we haven't done that yet. It's something that maybe we'll consider.
We're going to invite pXRF to the workshop too.
Yes.
Yes, in the case of chromium, you showed that you're presuming that it appears mostly in the chromate anion, but I'm wondering what kind of follow-up methods do you use to elucidate whether you have cationic chromium or you have chromate or dichromate?
So that would be a structural question, and XRF can't answer that. What I'm assuming is that chromium in some form or another is present. If I wanted to know what shape that chromium takes, I would probably take a small sample and use X-ray diffraction to get the crystal structure information. That would be the next step that I would think to do. But I'm not assuming what form the chromium is here. It's just that I know that lead chromate is a common yellow pigment. That's the assumption. So.
Another question loosely related to the chromium issue. Have you ever looked at ancient leather to try to see if there are tanning agents that you can spot?
So I haven't done that yet. What I did do is I have a book with various leather samples.
Mm-hmm.
And so this piece is it's buffalo and it's native tanned. So I took that sample book and I pulled out the samples that have any relationship to that, and I did blanks against that. And I took a background spectrum of just the unpainted area in the robe. So, and then also when I was looking at the other pigments, I didn't see chromium in any of those places and only in the yellow area. So it's a good question about what the tanning agents are, but we suspect that this is a brain tanned robe, and that's consistent with known samples that we have.